Howdy. This video is on standard electric potentials. For electrochemical reaction, the electric potential is used to determine if a reaction is spontaneous or non-spontaneous, and is related to delta G naught K and delta S universe. For reactions with positive potentials, the potentials equal the amount of volts that the reaction can produce if it's made into the battery. And so if a reaction has a positive potential, it means that it's going to be a spontaneous reaction. For reactions with negative potentials, that means a non-spontaneous reaction. And the potential is actually the amount of voltage that has to be applied to the reaction for it to proceed. And so actually for some electrochemical reactions, you can use them to get electrical energy, convert chemical potential energy into electrical energy. For others, you can actually convert electrical energy into chemical potential energy. And so what you should be able to do after watching this video is determine the potential for a reaction from the corresponding half reactions. You should be able to determine the potential delta G naught K for a reaction when it is reversed or if its coefficients are multiplied by a number. Given one of the following three parameters, potential naught, delta G naught, and K for a reaction, you should be able to determine the other two. So for each electrochemical reaction, a standard potential can be defined. Now that little superscript 0 means standard, similar to when we talked in thermodynamics about standard conditions. And so standard conditions for electrochemical reactions are just a little bit different. They're similar in that all soluble species are 1 molar. Any gas is constantly introduced at 1 atmosphere or 1 bar, which are pretty close. For electrochemical reactions, any metal must be in electrical contact, which we didn't talk about in terms of thermodynamics. Other solids must be present and in contact, and slightly soluble species must be at saturation. Now, potentials, the E naught is standard conditions, which means standard concentrations. Now, if you have non-standard concentrations, then you're just talking about the E. So just like in thermodynamics, where we had a delta G naught and a delta G were a little bit different. Delta G naught did not change with the reactions. E naught does not change as the reaction proceeds. E naught is a constant for a specific reaction at a specific temperature. And so for E, it does change as the concentration change. You can actually determine this experimentally. You can also just use the Nernst equation. So the Nernst equation is down below, and so E non-standard potential is equal to the standard electric potential minus RT over NF natural log Q. And so R is the gas constant, T is temperature in Kelvin, N is number of electrons being transferred in the reaction, F is Faraday's constant, and Q is the reaction quotient. And so again, E changes as the reaction proceeds, but E naught does not. Similar to, again, as delta G naught does not change and delta G does. And so for each electrochemical reaction, we can define a standard potential. If the potential is positive, its voltage corresponds to what the voltage of the reaction would produce if it's made in the battery. If the potential is negative, it is the voltage that would have to be applied to the reaction to make the reaction occur. And so we can look at the reaction of silver ions plus copper metal going to silver metal plus copper ions. It has a potential of 0.46 volts. And so if we made this reaction into a battery, the battery should have should produce a potential of 0.46 volts. Now if we swap products and reactants, now we have silver metal plus copper ions going to silver ions plus copper metal. Notice that our potential changed sign. Now the potential is negative, and meaning that to force this reaction to occur, we'd have to apply at least 0.46 volts. We can relate the potential to delta G naught, and so E naught equals minus delta G naught over NF. Delta G equals minus NFE, and so again, N is number of electrons being transferred in a reaction, F is Faraday's constant. Now the top equation to me is fairly important. What it shows you is E naught is equal to minus delta G naught over NF, and so that basically tells you that E naught is per electron. And so one thing that we'll see is that if we multiply the reaction times a number, it does not change our electric potential. It will change delta G. So you should remember for thermodynamics, if you multiply reaction times a number, you have to multiply delta G by that number. But because E naught is per electron, again, N is on the denominator for that equation, it does not change E naught. Also, delta G equals minus NFE because that negative sign. If E naught is positive, that means delta G naught is negative. So if E is positive, delta G naught is negative. That corresponds to a spontaneous process. If E is negative, delta G naught is positive, and that corresponds to a non-spontaneous process. And so you should make sure that you can calculate E naught from delta G naught and calculate delta G naught from E naught. And it's pretty straightforward, and so delta G naught is minus NFE. Now if we look at the reaction. Again, N is number of electrons transferred. Number of electrons transferred equals number of electrons in the oxidation step, which equals number of electrons in reduction step. And so the copper is actually being oxidized. Each copper is losing 2 electrons. You have 1 copper. And so in the oxidation step, you have 2 electrons. In the reduction step, silver ion, each silver ion is gaining 1 electron. You have 2 silver, so 1 times 2 is 2. And so you have 2 electrons in reduction step. And so that means you have 2 electrons being transferred. And so again, it's important to remember that number of electrons in the oxidation half reaction equals number of electrons in reduction half reaction equals the number of electrons transferred. And so for this reaction, N equals 2. F is Faraday's constant, 96,500 joules per volt mole. And our electric potential is 0.46. And so the volts cancel, and we're left with joules per mole minus 88.780. We should round that prior to 2. And so that gives us delta G naught equals minus 89 kilojoules per mole. And so we saw that we could relate delta G naught and E naught. Now, if you remember from your thermo, delta G naught equals minus RT natural log K. And so we should be able to relate E naught also to K. And so if we set minus RT natural log K to minus NFE, if we multiply by minus 1, and then if we divide both sides by RT, we get that. Now if we take everything to the power of E, we get that the equilibrium constant is equal to E to the power of NFE over RT. And so if E naught is positive, if our electric potential is positive, it means K is going to be large. If our electric potential is negative, that means K is going to be small. And so you should be able to calculate K from E naught or E naught from K. And so again, NFE over RT. And so N is 2 we saw from last time. F, 96,500 joules per volt mole. We have a potential of 0.46. R is the gas constant, 8.3145 joules per mole Kelvin. And temperature is always in Kelvin. And so we get, if the potential is plus 0.46, we actually get a equilibrium constant of 3.6 times 10 to the 15th. And so the more positive the potential is, the larger the equilibrium constant is. The more negative the potential, the smaller the equilibrium constant. And so it's really kind of cool reaction. Silver ions plus copper metal going to silver metal plus copper ions. And so basically, if you just take a beaker, you pour in a solution that has silver ions, and you put in a copper wire, you'll actually get silver metal starting to grow on that copper wire. You'll see a solution starting to turn blue as the copper ions form.
To demonstrate the copper-silver oxidation-reduction reaction, we're going to place a piece of copper wire in a petri dish and add silver nitrate solution to it. Here we can see the silver crystals beginning to grow, causing the copper wire to look gray and fuzzy. The copper wire you see under the microscope appears slightly out of focus, but as the silver crystals begin to grow and grow towards your eye, they will sharpen and become in focus. As the growth process continues, you begin to see the bright metallic crystals of silver metal. Here we see the contrast of the original copper wire to the wire after it has been in the silver nitrate solution. You'll also notice that the solution has turned from clear to pale blue. The copper metal has become the copper 2+ ion in solution, resulting in the blue color. The silver ion solution has become crystals of silver metal.
So again, kind of cool. And so if you have a positive potential, it means your delta G naught's negative, which means your K is large, which means the reaction is going to be product favored. And so silver ions plus copper metal going to silver metal plus copper ions is a spontaneous process. All you have to do is put a hunk of copper in a solution containing silver ions, and the reaction proceeds. Now, I mentioned if you multiply the reaction by a constant, it does not change the electric potential, because again, the electric potential is minus delta G naught over NF, and so basically the electric potential is per electron. But again, from thermo, you should remember that if you multiply the reaction times the number, you also have to multiply the delta G naught by that same number. If we multiply the initial reaction times 4, then we have to multiply the delta G naught by 4. But again, the potential does not change because the potential is per electrons. Now, if we multiply the reaction times the number, you should remember for the equilibrium constants, you have to take the equilibrium constant to that power. And so if we multiply the reaction times 2, the new equilibrium constant is going to be the old equilibrium constant squared. If we multiply the reaction times 4, then the new equilibrium constant is going to be the old equilibrium constant to the power of 4. But again, does not change the potential. Now, if we swap products or reactants, that will change the potential. And so it changes the sign of both the potential and your delta G naught. You should also remember that if you swap products or reactants, then the new equilibrium constant is going to be the inverse of the old equilibrium constant. Now, potentials for reactions are typically determined from the potentials of the oxidation and reduction half reactions. And so often what you have to do is you have to look at your reaction and be able to determine what is the oxidation half reaction, what's the reduction half reaction, find those potentials, and then you add them. Now, you can add potentials only when there's the same number of electrons in the two half reactions. And so we have 2 electrons in the oxidation half reaction, 2 electrons in the reduction half reaction, and so we can add those 2 potentials. Again, remember that in electrochemical reaction, you just have to transfer electrons from one thing to another thing, and so the number of electrons in the oxidation and reduction half reactions have to be exactly the same. Now, typically you're given tables of reduction potentials, and so these are all reduction potentials. Leo goes Gur, lose electrons, oxidation, gaining electrons, reduction. And so reduction potentials, something's gaining electrons. So notice that all the electrons are reactants, and so that corresponds to reduction potentials. Now, you can determine oxidation potentials by switching the products and the reactants. And so if you look at the bottom reduction potential, you have magnesium 2 plus 2 electrons going to magnesium metal, gives you a reduction potential of minus 2.36. Now, on the very bottom of the page, you have magnesium metal going to magnesium ions plus 2 electrons, and that gives you an oxidation potential of 2.36. And so to go from reduction potential to oxidation potential, you switch the reaction and you change the sign. And so the reduction potential for magnesium ion is minus 2.36. The oxidation potential for the magnesium metal is plus 2.36. Now, you cannot measure a potential of a half reaction by itself. You always have to have both oxidation half reaction and reduction half reaction. And so you cannot determine the reduction half reaction by itself. And so all reduction half reactions are determined relative to the standard half cell. And the standard half cell is 2 hydrogen ions plus 2 electrons going to hydrogen gas. That is the standard half cell. It's been defined as having a potential of 0.00 volts. And so all potentials are measured relative to that. Now, the more positive the potential, the more likely the reaction will actually occur. If we look at this table, the fluorine gas, F2, is the most readily reduced. It's on the top. It has the largest reduction potential. Now, the magnesium is the most readily oxidized because it has the largest oxidation potential. And so on the table, the magnesium would be the best reducing agent. Remember, the reducing agents are what's oxidized. And the fluorine gas would be the best oxidizing agent because the oxidizing agents are what causes the oxidation. And so oxidizing agents are what gets reduced. And so on this table, we can see that the magnesium plus 2 ion, we have the reduction potential of minus 2.36. We have the oxidation potential for the magnesium metal as plus 2.36. This comes from the half reaction at the very bottom. Now, a question you could ask yourself is, what about the oxidation potential for magnesium plus 2? Well, magnesium plus 2 does not lose an electron typically, and there is no oxidation potential for magnesium plus 2 on this table. Also notice that metals typically react by losing electrons, and so there's no reduction potential for the magnesium metal. Magnesium metals typically don't gain electrons, but on this table we do not have the magnesium metal reduction potential or the magnesium ion oxidation potential. In terms of magnesium, the only thing that we have is the reduction potential for magnesium ions and the oxidation potential for the magnesium metal. And so in general, nonmetals react by gaining electrons since they tend to have positive reduction potentials. In general, metal reacts by losing electrons, hence they often have positive oxidation potentials. And again, in the table, our reduction potentials, they get the oxidation potentials. We have to swap products reactants and change the sign of the reduction potential to get the oxidation potential. That's kind of interesting. Metals with negative oxidation potentials are less reactive. And so gold is the least reactive metal in the table according to the oxidation potential. Its oxidation potential is minus 1.52. And gold has oxidation potential of minus 1.52, platinum has oxidation potential of minus 1.2, and silver has that oxidation potential of minus 0.8. And so all a little bit less reactive, and so actually referred to as noble metals. Metal ions tend to get reduced, and so they tend to have a positive reduction potential. One question you could be asked is, which will more readily rust, iron or magnesium? Now, when metals react, they tend to lose electrons, so that means they tend to get oxidized. And so we need to look at the oxidation potentials for the iron and the magnesium. And so if we take the reduction potentials and swap it, we get the oxidation potential for the iron is 0.44, for the magnesium it's 2.36. And so larger oxidation potential means that the magnesium is more readily oxidized, it more readily rusts. And this actually has fairly important consequences. And so if you're going to have an iron tube, iron pipe, often what happens is you put a magnesium slug in electrical contact, and that way the magnesium will actually corrode before your iron pipe. It's also done in hot water heaters, and so the hot water heater, the shell is iron, and so you put a sacrificial anode, and the sacrificial anode can be aluminum or magnesium, something that's more reactive, and so the sacrificial anode gets corroded before hopefully the outside of the tank. Periodically you do have to check your sacrificial anode. On the right you can see a picture of a new anode, and then you see next to it one that was in a tank for a while, all corroded. But the reduction potentials are helpful because you can tell if a reaction is can be spontaneous or non-spontaneous. And so when you ask if it's spontaneous or non-spontaneous, what you have to do is find what is the oxidation half reaction, what is the reduction half reaction, add the oxidation reduction half reactions to find the potential for the net reaction. Now we see Cl2 is being reduced, and so we can use the reduction potential for Cl2. The zinc metal is being oxidized, so we have to flip the zinc reduction potential. And so that gives us reduction potential for chlorine is 1.36, oxidation potential for zinc is 0.76, and so we get a potential for the reaction of 2.12. And so that means the reaction is spontaneous, its electric potential is positive, delta G naught is negative, K would be much greater than 1. Here we have magnesium and zinc ions going to magnesium ions plus zinc metal, and so we have the oxidation of the magnesium and reduction of the zinc ions. And again, we have to flip the magnesium reaction to get the oxidation potential, and so reduction of magnesium plus 2 was minus 2.36, oxidation magnesium metal is 2.36, reduction of the zinc ions minus 0.76. We add those together, we got 1.6. Again, the potential is positive, so delta G naught is negative, and so K is much greater than 1, so we refer to that as a spontaneous reaction. We could also call it a product favored reaction. Here we have iron plus zinc ions going to iron 2 plus zinc, and so the iron's being oxidized, the zinc ions are being reduced. We find the corresponding potentials in the table. Again, we have to flip the iron because we need the oxidation potential, and we get a potential of minus 0.32. And so that's a non-spontaneous reaction. Our electric potential is negative, delta G naught is positive, K would be less than 1. We refer to this as a reactant-favored reaction. And another interesting question that we could ask ourselves is which of the following metals will spontaneously react with hydrogen ions? We could also think about, okay, so any strong acid, you form hydrogen ions. The reduction potential for the hydrogen ions plus 2 electrons goes to hydrogen gas. That has a potential of 0. And so basically the question is which of the oxidation potentials when we add to the hydrogen ion potential gives us a positive potential. And so it turns out that all the metals below our standard half cell reaction, when you flip them, give you positive oxidation potentials, and so they should spontaneously react with hydrogen ions. The metals above the standard half cell, when it flips, will give you a negative potential, and so of those 5 metals, silver should not spontaneously react, but iron, zinc, aluminum, and magnesium should all spontaneously react.
Equal amounts of magnesium, aluminum, iron, and zinc are each covered with 100 milliliters of concentrated hydrochloric acid at room temperature. As the acid begins to react with the metals, hydrogen gas is liberated, and a solution of the chloride salt of the metal remains. Also, the temperature begins to rise. Because we have used the same amounts of metal for all the reactions, we can compare them. It is apparent that although the reactions are similar, they liberate different quantities of heat and proceed at different rates.
And so the video made a mistake by implying that you could actually
Equal amounts of magnesium.
relate the rate of the reaction to the potential. You cannot relate the rate of the reaction to the potential. Okay, so thermodynamics is different from the kinetics. And so, for instance, the aluminum, often aluminum has aluminum oxide layer, and so that's going to be typically a slower reaction than if you had something like zinc. But please remember, thermodynamics and kinetics are different, and so even if you have a large potential, does not mean the reaction is fast. And so here we have the potentials for the metals plus hydrogen ions, and so we see that silver with the hydrogen ion gives you negative potential, and so it's a non-spontaneous reaction. So silver doesn't really react readily with acids. The iron, the zinc, and the aluminum all have positive potentials, and so they all react readily with the acid. And so a question we could ask is, will a modern penny, which is copper-plated zinc, dissolve in concentrated HCl? And so HCl has the hydrogen ions. Now the chloride ions have a negative oxidation potential, and so we're just not going to worry about them because they're not that reactive. And so for HCl, we'll just think about the hydrogen ions, and then if we think about the copper, we're going to have to flip it, and so that would give us a negative oxidation potential, and so that gives us negative potential for the reaction, and so copper should not spontaneously react with HCl. Now if we take the zinc, we look at the zinc and we see we have a positive potential, and so zinc will spontaneously react with HCl. Now it's kind of cool, if you take a modern penny and you scrape off the edge a little bit and you put in HCl, what actually happens is it consumes the zinc on the inside of the penny but doesn't consume the copper on the outside. And so what this tells you is that metals, in terms of reactivity, are not all the same, and often you can tell reactivity based on the potential. Now we could also ask, okay, what about nitric acid? Well, nitric acid is hydrogen ions plus nitrate ions, and so notice that the nitrate ion is in reduction potential above the copper. And so actually if we combine these two if we combine the reduction potential of the nitric acid with oxidation potential for the copper, we get a positive potential. And so HCl will not readily react with copper, but nitric acid will readily react with copper. And so not all strong acids are the same. And so we classify both HCl, nitric acid as strong acids, but nitric acid can actually dissolve more types of metals than hydrochloric acid because nitric acid is a better oxidizing agent, has a larger reduction potential. Now we can actually enlarge our table a little bit, but again, please remember nitric acid will dissolve more types of metals than hydrochloric acid because it's a better oxidizing agent. When you're asked about nitric acid, you have to use the half reaction in red. Perchloric acid can actually dissolve more types of metals than the nitric acid. Hydrochloric acid, nitric acid, perchloric acid, they're all classified as strong acids, but again, in electrochemistry, we'll see that perchloric acid is a stronger acid. Well, it's not stronger, it's a more reactive acid and can actually dissolve more metals. And so nitric acid could not dissolve platinum, but perchloric acid can actually dissolve platinum. And so if you're asked about perchloric acid, make sure that you use a half reaction in red. But not all strong acids are the same. When you're asked about hydrochloric acid or any strong acid, you use the half reaction in blue. And again, chloride ion is not very reactive, and so we just ignore it. Interesting question we could ask is there any way of dissolving gold? And so not even perchloric acid could dissolve gold, but what we could do, it's got a negative potential. Nitric acid also, if you try to react nitric acid with gold, it's going to have a negative potential. It's not going to be very successful. But if we take that nitric acid and we add some chloride ions, say from hydrochloric acid, what will happen is the nitric acid can dissolve a little bit of gold, and then that gold ion will react with the chloride ion to form the gold chloride complex. And so that will shift that reaction to the right. And so aqua regia, which is a mixture of nitric acid and hydrochloric acid, is actually able to dissolve gold, again because as the nitric acid dissolves a little bit of gold, the gold ions are consumed, pushing that top reaction to the right, and more of the gold actually gets consumed. And so please remember, standard electric potentials can be used to determine if reactions are going to be spontaneous, non-spontaneous. It's related to delta G naught, K, and delta S universe, whether or not the reaction's product favored or reactant favored, also whether or not you can use the reaction for a battery or not. I hope that was helpful.